Greetings. Welcome to today's session. So, if we briefly recap what we were doing in the last session, we were looking at having what to say this closed loop control system design, and we tried out for a couple of examples. And as we are aware, we need to look at the let's say position of the closed loop pole in the let's say in the desktop plane, and we need to find equivalent conditions, right, on the controller gain that will ensure that we should be essentially are able to stabilize the closed loop system. Okay, so given that, the question that becomes is the following: how do we come up with some general conditions or general methods, so which will ensure that any given nth order polynomial will be a Hurwitz polynomial. So that is, like, if we are calculating the closed loop characteristic polynomial, and we get an nth order polynomial in general, like, how do we decide the distribution of roots of this polynomial? Like, the impact will be on control design, because we will be able to find conditions on the controller gains that will ensure that the closed loop poles are in the left of complex. Okay, so let's answer this question, and then we'll come back to a specific question. So the question that we are asking is what is written here. Consider a nth order polynomial. D of s is a naught s power n plus a1 s power n minus 1 all the way till an. The question that we are asking ourselves is, like, how can one determine the distribution of roots of this polynomial? Okay, of course, without calculating that. All right, so that is very important. All right, so the response is the following. Okay, answer. The first step is that, like, we need to check whether all coefficients of the polynomial d of s, okay, that is a naught, a1, all the way till an, are non-zero and of the same size. Okay, so that is the first check. So this is a necessary condition, but it's not sufficient. Okay, so, but this is necessary. Okay, I will explain to you what is the difference. So this is a necessary condition for the polynomial d of s to be Hurwitz. So what is the necessary condition? If the necessary condition is satisfied, doesn't mean that the polynomial is Hurwitz. But then if the necessary condition is not satisfied, then the polynomial is certainly not Hurwitz. Okay, so that is the meaning of necessary condition. Okay, so that's why necessary condition becomes important. So if we apply this necessary condition to this polynomial, we can immediately see that the coefficient of s squared is 0, right? This implies that PI controller will not stabilize the closed loop, right? So I'm just going back to the example that we were working on in the previous class. So where we tried a proportional controller, we figured out that the proportional controller will not work. Then we went to the PI controller, right? So what we have figured out is that even the PI controller will not work. Just to quickly recap what we were doing, we were looking at this problem, 1 by s squared minus 1. That was the Planck transfer function. We were trying to stabilize it using unity negative feedback. We saw that using a proportional controller, it won't work out. So we tried out a PI controller, and with the PI controller, we ended up with the closed loop characteristic equation, right? And now, what we based on the necessary condition that we discussed just now, we can immediately see that the PI controller is not going to stabilize the closed loop system. Why? Because we are essentially missing the coefficient of S square. The coefficient of S square is 0. So that essentially violates the necessary condition. So the moment it violates the necessary condition, we know that this is certainly not true. So the PI controller will not stabilize the closed loop system. I hope the conclusion is clear. Okay, so this is only the necessary condition. Now, what will be sufficient to look at the sufficiency condition? We construct what is called as a Rouse array. So let me explain what the Rouse array is in general, and then we will do a bunch of examples to learn further. Okay, so that's something which. So how do I construct the Rouse array? Like we construct the Rouse array by doing this. So if we, let's say, s power n minus 1, s power n minus 2. Okay, first what we do is that we write down all the powers of s in descending order. Okay, starting from s power n. So we do s power n minus 1, s power n minus 2, s power n minus 3, all the way till s power 1 and s power 0. Okay, so that's what we go to. And then what we do is that we essentially take the first two rows and we fill out these first two rows with the coefficients of the polynomial that we are considering. So the coefficients of the polynomial that we are considering are A0, A1, A2, A3, A4, A5, A6, A7, and so on, right? How many other coefficients we have? We just keep on writing them, all right? So that's what we do, all right, in this first step. Okay. So then what we do is that we go to the third row and we fill the third row with the coefficients B1, B2, B3, and so on, right? And how do we do this? To calculate B1, what we do is that we look at the previous two rows, we multiply A1 and A2, subtract the product of A0 and A3, and divide by A1. Okay. So essentially, to calculate what is B1, we have A1, A2 minus A0, A3 divided by A1. Okay, so that's one. Then to figure out B2, we multiply A1 and A4, we subtract the product of A0 and A5, and we multiply by A1. So you will get the hang of it, right, as we keep on going. So we will have A1, A4 minus A0, A5, okay, divided by A1. Okay, so that's all. All right. So like this, we keep on moving ahead, right? As we do. All right. So we calculate B1, B2, and all those coefficients. Okay. So you see that to calculate the coefficients in any row, what we do is that we essentially look at the previous two rows. Okay, and we keep on applying this formula. Okay, continuously. So we exhaust all the coefficients in that particular row. All right, so that's the policy we will do. So similarly, if you go and look at the row of s power n minus 3, we calculate C1, C2, C3, and so on. Right? By now, I'm sure we will see the pattern. If I want to calculate C1, then what will I do? I will take the two rows immediately above it. Right? Those are the s power n minus 1 and s power n minus 2 rows. So what I do is that to calculate C1, I multiply B1 and A3, subtract the product of A1 and B2, and then divide by B1, right? To similarly calculate C2, I multiply B1 with A5 and subtract the product of A1 and B3 and divide by B1. Okay, so that's what we do. All right. So like this, we keep on moving ahead. So let me write down the equations for C1. C1 will be B1 A3 minus A1 B2 divided by C1, right? And C2 will be equal to B1 A5 minus A1 B3 divided by B1. Okay, and so on. Okay, so we keep on doing these things iteratively, right? So essentially, we keep doing these calculations, right? This set of calculations. So like this, we keep on filling this array. Okay, we go further and further. Okay, so like this, we go till s power 0. So we are going to do a few examples, right? So then things will become clear. Now, once we fill the so-called routes array, so this is what is called as a routes array. Okay. Once we fill the routes array, what we do is that, like, we look at the first row of the routes array. This one. Okay. So once we fill the routes array, and then we look at the first, sorry, not the first row, first column of the routes array. Okay. Sorry about that. This is the first column of routes. All right. So this is the first column of the routes array. Now, what we do is that in this route array, once we fill it in this way, the condition is that the first column of the routes array should not have any zeros, nor there should not be any sign changes. Okay, the first column of the routes array. Okay, so that is very important. So let me write down what is the condition. So the necessary and sufficient condition for the polynomial d of s to be equal with is that there should be no sign changes in the first column of the rows array. So the first column of the rows array should have all coefficients, of course, to be non-zero and of the same sign. Okay, then only the polynomial d of s is full width, or in other words, all the what to say, roots of that polynomial will be in the left half complex. Okay, and this is what is called as the Routh criteria. Okay, so this is what is called Routh stability criteria or the Routh criteria. Okay, as applied to control theory. So in general, one can use the Routh criteria to figure out the distribution of roots of the polynomial. But from the perspective of our course, okay, so our application is on control system design. And so what we are going to do is to use this criteria to figure out whether the closed loop system is stable or not. Okay, so that's all we are going to do. All right. Okay. So now what we have is the following. Okay, so once we have this, we are given a polynomial. First, what we do is that we do two things, right? First, we check whether all the coefficients of the polynomial are non-zero and of the same type. Okay, that is the first step. And once we do the check, what we do is that, like, we construct the route array, we complete it, and then we look at the first column of the route array. And if there are no sign changes in the first column of the route array, then the polynomial is full. Okay, so that is what is called as the Routh criteria. Okay, for stability. All right, so that's something we have. Okay, so now what is the corollary? What is an immediate follow-up statement from this condition? So the corollary is the following: the number of sign changes in the first column of the route array is equal to the number of routes of D of this in the right order. Okay, so that's what we have. Okay, so the corollary from this statement is that we have we look at the first column of the rows array. If there are sign changes, and we count the number of sign changes, right, of the in the first column, then whatever we have, the number of changes is equal to the number of rows in the first, in the right of this, okay, in the complex. Okay, so that's what. All right. Okay. So that's a corollary of this particular condition, right, or the row stability. Right. So let's apply to a couple of examples. Then we will understand it better. Right. So let's do this example so that all of us will understand this condition. So see, if you look at it, the Raoult's criteria is a result from complex variables. You know that in general we can use for figuring out the distribution of roots of a given polynomial, right? So we are using it to figure out if the polynomial is Hurwitz, and to be very specific, if the closed loop characteristic polynomial is Hurwitz, because that is of our interest, right? Isn't it? So when we design the closed loop. So let's now consider two polynomials. Let's say d1 of s. D1 of s, let's say, is s cubed plus s squared plus 2s plus 1. Right? And let's also consider another polynomial d2 of s, which is s cubed plus s squared plus s plus 2. All right. So what is the change that I have done in this case between what is the change in D1 and D2, or what is the only difference between D1 and D2 that you can identify? I'm sorry.
S coefficient and the constant value.
Yes. So if you look at it, you can essentially we have essentially swapped, like the coefficient, right, of the s term and the constant term, right? So that is what we have done, right, as far as d1 and d2 polynomials are concerned. Very good. So now, do you think the necessary condition is satisfied? What is the necessary condition? All coefficients must be non-zero and of the same sign. Do you think that is satisfied?
Yes.
Correct. So we can immediately see that both are third order polynomials, and we can immediately observe that all coefficients of d1 and d2 of this are non-zero and of the same sign. Okay, so that's one important observation that we can make. Now let's construct the rows. Okay, and then let's figure out what is happening, right? So let's construct it. So let's construct the rows array for d1. So we have s cubed, s squared, s power 1, s power 0. So how do we construct? So once again, we fill up the first two rows with the coefficient. Please watch what I'm doing. So I start from the s cubed coefficient, which is 1. S squared coefficient is 1. The coefficient of s is 2. And the constant term is 1. Right? That's it. Like we are done. Right? Isn't it? So what we do is that now to figure out what is happening in the s power 1 row, we take the first two rows. What we do, we multiply 1 with 2, right? And subtract the product of 1 and 1. So 1 multiplied by 2 will be 2. And subtracting 1 from it, we are going to get 1. Sorry. And we divide by this number. Okay. Whatever is at the beginning of the row. Okay. So that number is 1. So what is 1 divided by 1? I'm going to get 1 as the answer. Okay, so that's it. I hope it is clear, right? So any questions? How I got 1? I'm sure it's what to say, clear as to how we got it, right? So after this, I don't need to fill out any other what to say coefficients because there are none. Because after this, you can see that there is nothing here, right? So I don't need to proceed with this calculation. Like I am done with this calculation, right? So now what we do is then, like, we go to the s power 0 row. For the s power 0 row, once again we take the two rows immediately above it, right? Which will be s squared and s power 1. So what do we do now? We multiply 1 with 1, right? Subtract the product of 1 and nothing here. So if you have an empty cell, you take it as 0, right? And divide by this element, which is 1. So the answer once again becomes 1, right? So we get 1 as the. So of course, in this case, it's just a coincidence that we are getting 1 as the entry in all the first column, but it's not persistent. Okay, just a specific case. All right. So now, if we look at this, we look at the first column.
Professor, one question.
Yes, please.
For the S naught, 1 into 0 minus 1 by 1, right?
1 times 1 minus 1 times 0. Right. So we start from the s power 1 row. Right. So let me repeat the sequence. Okay. So what we do is the following. Let me repeat the sequence. It is this one multiplied by this one. Okay. Yeah. All right. Minus the product of this and then divide by this one. So since S, what are the two rows immediately above s power 0, s power 1 and s power 2. So you need to start the multiplication with the elements in the s power 1 row. Okay. So that's the solution. Okay.
Okay.
So now, if you look at this in the first column, right, of the rows array, we can see that all coefficients are non-zero and there are no sign changes, right? Isn't there? So you can see that all numbers have a positive sign. Okay, for the time being, let's not worry about the fact that all the coefficients happen to be +1. Okay, yeah. But however, we can always see that we have the coefficients, right, to be positive, right, in the first column. Okay, so then we can immediately figure out that this polynomial is Hurwitz, right, by using the Raoult's criteria. That is, if you observe the first column of the Raoult's array, we can immediately observe that there are no sign changes in the first column of the Raoult's array. So this implies that all three roots of D1 of S, okay, lie in the LH. Okay, so D1 of S is Hurwitz. Right? I hope this example is clear. All right. So now let's do for D2 of S. Okay, let's do the same thing for D2 S. So once again, we construct the Raoult's array. We have S cube, S square, S power 1, S power 0. We take the first two rows. We fill with the coefficients of the polynomial. Coefficients are 1, 1, 1, and 2. Right? So please stop me if there are any questions. But I hope this exercise is clear. Right? So what do we do in order to figure out the coefficient in the s power 1 row? We take the two rows immediately above it. Then what we do? We multiply this one with 1, subtract the product of 1 and 2, and then divide by this one. Right? So what will I get? I'll get 1 minus 2, which is minus 1. Minus 1 divided by 1, I will have minus 1. Okay? So that is the coefficient in the s power 1. And I don't need to do anything more because I don't have any other elements, right, in the to process, right, in the row above. Then for s power 0, I consider the s power 1 and s squared row. So first I multiply minus 1 with 2, subtract the product of 1 and 0, which will be minus 2, and then I divide by minus 1. So if I divide minus 2 by minus 1, what will I get? I'll get plus 2. Right? Is it normal? Okay. So now I look at the first row, the row cell. What can you say? Oh, sorry, not first row, first column. Yeah. What can we observe?
Change in sign.
There are sign changes, right? How many sign changes can we count?
1.
Okay, so let's count them. Okay, so we can see that there is one sign change from 1 to minus 1. Okay, so that is one sign change. But there is another sign change from minus 1 to plus 2, right? Isn't it? Okay, see, first in the second, from first second element to the third element, we have one sign change, and from the third element to the fourth element, there is another sign change. Does everyone agree? So this implies that there are two sign changes in the first one of the root cell. Okay, so what does this imply? Two roots of D2 of S lie in the right half complex. Okay.
So, Professor, in case S0 is minus 2, so will it be only one sign change?
Exactly. If S0 were minus 2, we need to count as only one sign change. Okay. Yeah, that's right.
Yes.
Okay. So essentially, it depends on how you need to count a sign change as the name indicates. From positive to negative is 1. From negative to positive is also 1. Okay. All right. So please note that the necessary and sufficient condition is that all the elements in the first column should have the same sign. So they can all be positive or they can all be negative. Okay. So either way is fine. All right. But if there is a sign change that indicates a root in the right of complex plane, the number of such sign changes will be the number of roots in the RHP. All right. So we can immediately see that. See, this is why as we go to higher order polynomials, we need to be careful, right? So ensure we have learned an important lesson from this exercise, right? That is, we have two polynomials, D1 of S and D2 of S. Both are third order polynomials. Those are satisfy the necessary conditions. And the change that we have done seems to be very minor, right? We just swap the coefficient of the F term and the constant. However, the impact was phenomenal. That is, while for D1, we had all the three roots in the left of complex plane and D1 of S was full width. D2, it's not full width, right? So we have its roots in the right of plane, right? So we can see the challenges associated with it, right? So, and we can see the value of this criteria, right? So because we can immediately realize that, by using this criteria, we are able to get, very important information, right, on how, the roots of the polynomial will be distributed. Okay, so I hope this exercise is clear. Any questions? On this? Fine. Okay. So now one important thing to note. Okay, let me write a note. For polynomials till order 2, okay, so for polynomials till order 2, there is still second order polynomial. The condition that all coefficients be non-zero and of the same sign is both necessary and sufficient. Okay, so this is an interesting condition, right? Is it not? That is, if we have polynomials to order 2, that is like first order and second order polynomials, we don't even need to form the root array. Okay, by just looking at the polynomial, we can conclude about the distribution of it. So let's say we take n equals 1, right? It's very straightforward, right? Let's say we have the polynomial d of s to be a naught s plus a1, right? So that's the first order polynomial. We don't even need to do anything. We can directly calculate the root, and the root will be minus a1 by a naught, right? Immediately we can see that if you want the root to be in the left of complex plane, we need both a naught and a1 to be non-zero and of the same sign, right? If either one is 0, we won't have the root in the left of plane, right? And if the sign of a1 and a0 are different, then obviously the root will not be negative, right? So we can immediately observe that, right? So that's straightforward. So similarly, if we take a second order polynomial, so d of s to be a second order polynomial, a0 s squared plus a1 s plus a2. So once again, we will see that if we form the root array, s squared, s power 1, and so on. I'm just forming the root array just to explain the result. So we can immediately see that we can write a0, a1, a2. The coefficient in the s power 0 row, what we do, we multiply a1 and a2, subtract the product of a0 with 0 and divide by a1. So what will we get? We will get a1, a2 by a1. So we will just get a2. Okay. So you can immediately see that we get a2. And if you look at the first column, what we observe, we have a0, a1, a2, right? So the necessary condition is both sufficient, right? So necessary condition is also sufficient. Okay, I should say that, right? So I hope we can immediately observe, what we have. All right. Okay. So you can, I'm sure you can immediately figure out why till polynomials till order 2. The condition that all coefficients must be non-zero and of the same sign is both necessary and sufficient. All right. So I think I hope this is clear. All right. Okay. So any questions on this? Okay. So now we will go back to our example. Okay. So we have learned this Route's criteria. Let's start applying it. All right. So we go back. Let us go back to our example and try PD control. Design or attempt. Yes. Proportional derivative control. So what was our example? Our example was this, one with the transfer function being 1 by s squared plus 1. Sorry, 1 by s squared minus 1, right? So this was the example that we were dealing with. So we saw that this plant cannot be stabilized using proportional control, point number 1. Okay. And this plant cannot be stabilized using PI controller. How did we figure out? By using the necessary condition of the Route's criteria that we studied today. Okay. So let's consider a PD controller. Okay. So let's recall that P of s was 1 by s squared minus 1. All right. So now the controller transfer function C of s is going to be equal to KDS plus KT, right? So that is the transfer function of a PD controller, right? So this implies I'm just doing the same standard calculation, right? So nothing more than that. So G of s, which is going to be equal to C of s times P of s, is going to be KDS plus KT divided by square minus. Okay, so this is what we have. So now the closed loop transfer function in this case will be equal to G of s divided by 1 plus G of s H of s. H of s is unity. So G of S is going to be equal to KDS plus KP divided by S squared minus 1. The whole thing divided by 1 plus KDS plus KP divided by S squared minus 1. Okay, so this will give us, if you look at the answer, KDS plus KP S squared plus KDS plus KP minus 1. Right? I hope what I'm doing is clear to everyone. Right? I'm just taking the LCM and then like we'll cancel out the term S squared minus 1. Right? So I hope it's clear to us. Right? So please stop me if there are any questions. Okay? So this is one. Yeah. So this implies that the closed loop characteristic equation, because we need to look at the closed loop characteristic equation. Right? The closed loop characteristic equation is going to be S square plus KDS plus KP minus 1, right, equal to 0. So that is going to be the closed loop characteristic equation, right? So we can immediately see that this is a second order polynomial, right? So what is the necessary and sufficient condition for the second order polynomial to be held with? We just looked at it.
All the coefficients are positive and
all the
coefficients are zero on the same side.
Very good. All the coefficients must be non-zero and of the same sign. Okay, so please, I can't reiterate this enough. Okay, it is only same sign. Okay, it doesn't say whether they should be positive or negative. What it means is that like if all the coefficients are all positive or they should all be negative. Okay, either way. All right. So now, if you look at this particular polynomial, it's a second order polynomial. The coefficient of S squared is plus 1, right? So the coefficient of S squared is already positive. So there are two more coefficients. So KD and KP minus 1, right? So consequently, what can we say? We can say that the closed loop system is stable, is Bibot stable or asymptotically stable when KD is greater than 0 and KP minus 1 is greater than 0, right? We should satisfy both the conditions, only then things will work. Okay, so this means that a proportional derivative controller, a PD controller, would stabilize the system. For KP greater than 1 and KD greater than 0. Okay, so we can immediately observe that the PD controller works in this case, right? So we have this sort of region, right, or choice for the controller gain, wherein we have the proportional controller stabilizing the closed loop system. Okay, so that's very, very important, right? So I hope it is clear, right? So if we draw the controller parameter space, please recall what is the controller parameter space. Controller parameter space means we draw the the range of controller parameters given by this constraint. So if we plot this controller parameter, so KD greater than 0 will be this half plane, right? So one above this axis, right? Now KP greater than 1 will be this, right? So we draw the vertical line at KP equal to 1, okay? And we have KP greater than 1 to be this to the right of it, okay? So consequently, all the points, okay, which the entire region, okay, which is the intersection of the two regions, will be the feasible region, right? Where we can use, wherein we can use you can have the choice, okay, of the controller. So this is a feasible region, okay. Okay, so as we discussed, this is a controller parameter space. Okay, so if someone asks you to draw the controller parameter space, this is what they're expecting. Okay, when you design the closed loop system. Okay, so this is the controller parameter, okay, for this particular problem. All right. Okay. So any questions? No?
Sir, can you come again? Why PI controller will not stabilize the system?
Why PI controller will not stabilize the system? Let's go back. So I'm just going back here, right? So I hope you can look at what we derived with the PI controller, right? The closed loop characteristic equation is S cube plus KP minus 1S plus KI equals 0, right? So you can eventually see that there is the coefficient of S squared is 0, right? Isn't it? So the necessary condition that all coefficients must be non-zero is violated. So there is no way you can make the coefficient of S squared appear as non-zero by adjusting KP and KI. Can we? Right? So that's why the PI controller is not work. Okay? Is that clear?
Okay.
So that you can immediately realize that there is no value of KP and KI, which will ensure that the S squared coefficient will appear in this equation, right? So the S squared term is 0. So the necessary condition in the Rhodes criteria itself is violated. Okay? So that is what happens. Okay, like when we have one coefficient to be 0. Okay. So that means that there is no way this polynomial will be Horvitz. So that what that means, that means that there is no value of KP and KI which will ensure that the corresponding closed loop system is stable. That's why we concluded that the PI controller will not be able to stabilize the given system. Okay, so I hope that answers the question. Okay. Any other questions? So I'm going to leave you with two broad queries. Okay, the first query is something I want you to think through. So what happens if there is a 0 in the first column of the row? Okay, we did not discuss this thing, but you just think about it. Okay, so and we will, when we encounter it, we will figure out what happens. Okay, so what happens if the first entry, okay, or the first column in a row of the rows array is 0. Okay, so that is question number 1. Question number 2, which I want you to essentially try out, and we will discuss this tomorrow, is the following. I want you to consider a plan whose transfer function is 1 by S squared plus. So you can immediately see that the poles of this plant are at plus or minus J, right? So we are having a pair of poles on the imaginary axis, right? So what I want you to do is the following, right? Essentially consider this plant and design a closed loop control system, for this particular plant. Okay, so the poles should be at plus or minus. Okay, so this is what we need to do, right? And essentially, I will leave this to you as an exercise. Please try out this problem, and then we will discuss this in our next. Fine. Any questions on what we learned today? Okay. So if not, I will close today's session here, and then we will continue from here in the next class. Thank you.